Hello. I've worked out an example for unbalanced loads. So, this example is in your slide. So, bisitahin nyo na lang. Basically, what I have here is three loads drawing three different powers each. So, for loads 1 and 2, you have uh, different loads drawing different currents at different power factors. You have another load which is drawing a certain real power at a certain power factor. All of them are lagging, so all of them are inductive loads. So loads 1, 2, and 3 are at AB, BC, and AC in that particular order. So you have the line-to-line voltage 230 volts with the system being in ABC sequence. So I think for this example, since it is not given, we'll be using the voltage at AB as reference. So that means your voltage at AB will be 230 for the line-to-line voltage. Since it will be our reference. Okay. So for this example, we want to get the total power, total apparent power, total power factor to system, and then later on we'll be getting the line current lines for lines A, B, and C. Now, since your voltage AB is reference and the system is in sequence, so that means your VAB is at 230 angle 0. Then you have VBC and VCA, which is 230 angle negative 120, and VCA, which is 230 angle 120. Now, according to the description of the loads, they are connected in any two lines, A, B, B, C, and CA, and in this actual configuration, so it's actually in delta. So you have this system with the loads connected between any of the two lines, three loads, and then the line currents are these line currents. Then you have these load currents. So the direction of the load currents are under the assumption that between A and B you have A as positive, B is negative. So for that load, which is load 1, the current goes from positive A to B, with A being positive of higher potential than B. Then you have B higher potential than C for the load between B and C, and you have C higher potential than A for the load between C and A. So the solution for the total power is quite simple. It's just the summation of the three powers. So you just want to solve for the power at load 1, power at load 2, and the power at load 3. You get the sum of that, you get the total power of the system. Now for each loads, the power is just the voltage times its corresponding voltage and current conjugate. So for example, if you have load 1, you know that the voltage at load 1 is VAB since it is connected between A and B. So this is load 1, so the voltage of that is this voltage, which is VAB, that's 230 angle 0, and then the current of that is this current which is I of load 1. If you look at the given, the current is actually given, however it is just given as 106. So that 106 is not enough because it's just the magnitude of the current at load 1. If you solve for this equation, S is equal to VI conjugate, what it will look like is 230 angle 0 for the voltage times the conjugate of 106 angle sum theta, which is theta of load 1 conjugate. Now there are lots of ways to solve for that theta, but we'll deal with that later. But if you look at the given again, the power factor is given, so that power factor is actually the power factor of the load. So this 0.78 is the power factor of the load 1. Therefore, from that power factor itself, we can already get the angle of the apparent power. So we don't really need to solve for this theta here, because we already you can already get the angle of S as the angle of the power factor, which is our cosine of 0.78. So what you'll be needing on actually is just the magnitude of the voltage and the magnitude of the current, which is 230 and 106. So the S at load 1 would be 230 times 106 angle, arc cosine of 0.78. Now that is for load 1. For load 2, you do the same for load 2, and then you have this power. So these two loads are inductive because they are both because their power factors are both lagging. So you have these powers, load 1 and load 2, in rectangular and polar form. Now if you have for load 3, what we have is the real power. So we'll be using a different equation here. For the load 3, you can get the magnitude of the power actually from the formula of the power factor. So this one. So your power factor is equal to your power divided by magnitude of S. So you can get the magnitude of S as your power 28.4 kilowatts divided by the power factor, which is 0.77. Now, that's the magnitude of S. Again, for the angle, you can use the power factor, our cosine of 0.77. So you can get the S of load 3, the apparent power of load 3. Now you know all of the apparent powers for loads 1, 2, and 3. You can get the total power as total as the summation of the 3, which will give you this power here as total, with 74.1 kilowatts as the total real power and 57.48 as the total kVAR as the total reactive power. Now that is inductive because it's positive. For the power factor of the system, it's just the cosine of the total of the angle of the total power. So it's cosine of 37.76 degrees. You can also get this as you can also get that as the total power, which is 74.1976 divided by the magnitude of S, which is 93.8593 kVA. So that's it. That's basically the total power and power factor. Now for the line currents, if we go back to this diagram, we want to get the line currents IA, IB, and IC. So to get that, you can perform KCLs at this node, and at this node, such that, for example, your current IA is just the KCL of this and this current. The IB is just the KCL of this current, and so on and so forth. For instance, IB is equal to I load 2 minus I load 1. So this is IB. Current at line B is load 2 minus load 1. So if you go back to the given, you already know load 2 as 142 amperes and load 1 as 106. However, take note that those are just magnitudes. Therefore, you cannot equate IB to 142 less 106 because that will be subtracting your vectors improperly. To do that, you'll be needing the angles of load 2 and the angles of the currents at load 2 and load 1. So yeah. Now there are lots of ways to solve for that angle. Well, first you can solve for that angle. The easiest one would be this one. You can solve for that angle using the angle of the power. Like for instance, you want to get the angle of load 2. Of the current at load 2. Sorry, I forgot this negative here. So it's basically the negative of the theta S of load 2 and theta V of load 2. Minus theta V of load 2. So if we go back to the given to the previous page. Where is that? Ito. If you go back here, you get the angle of load 2 as 34.91. So that's 34.91. And then the voltage, the angle of the voltage is negative 120 because load 2 is at VBC. So those are these these angles here. Sorry, again, I forgot this negative here. Okay, so if you solve for that, that will give you negative 154.91. So the current at load 2 is not 142 but 142 angle negative 154.9152. So that's how you solve for the angles. You may solve for all of the angles for loads 1, 2, and 3 for the currents for you to completely get the currents at the loads. But I guess the simplest one would be to solve for I, since we already know S. Well, it's just your power formula. If you rearrange the variables, the parameters, you'll just get I as conjugate of S over V. Now you already know the you already know the power at each load 1, load 2, and load 3, and then you know their corresponding voltages VAB, VBC, and VCA, so you can solve for the load currents IL1, IL2, and IL3. Of course, don't forget the conjugate. Now, perform KCL, you get IA, IB, IC. So that's basically unbalanced loads. And yeah, so I'll see you soon. Okay, but maybe